preview that we were going to be able to do that when we got to the next section. So now we're here, okay? 5, 4 complex numbers. Before, if you had a negative number and you tried to take a square root, you punch it in the calculator, you get an error message. Well, we have a way around that now. So, whenever we're trying to solve some sort of a quadratic equation, that's just a fancy way of saying it has x squared, sometimes you're going to get something with negative. And before we couldn't solve it, now we're going to be able to. So, like it says here, x squared equals -1 has no real number solution because, well, if you take the square root of -1, it's not real. However, we now have this imaginary unit, and some of you think mathematicians just imagine all this stuff anyway, called I. Okay? It's not a variable, it's actually a value, it's actually a number. So what you see right here with these two things are going to, oops, not with that one, with that pen not working. These two are going to be the two things that we use to actually solve these. Understanding that I itself is the square root of -1. Well, if I would, bless you, if I would square that, I'd find that I squared and square root or inverses is -1. There's actually a number I can use with this. So, for instance, when we start looking down here, before if I got the square root of -5 as an answer, I'd either say I can't do it or that's as far as I can go. Not anymore. What you're allowed to do at this point, and please excuse my humor sometimes on things like this, but it makes things stick, is that whenever you see a square root of a negative number, think about the fact that you could just pull an I out, okay? It's kind of a strange thing, and I'm not going to start throwing it off the walls like I do sometimes, but that's kind of a way to think of it. That you're pulling an I out, and then whatever's underneath becomes a regular radical. So like, for instance, if you had something, as we get down here into our problems, like the square root of -9. Again, the first step with these always is to pull an I out. And that pulls the negativity right out of my square root. Because now, what's the square root of 9? 3. So the square root of -9, I can actually come up with a solution now. It's 3i. Okay? No plus or minus here because we're not trying to solve for a squared term yet. But anytime I see this, my first step is always to pull the I out. Okay? That changes whatever's underneath the radical to a positive, and sometimes this may be as far as I can get. If I can't break down the radical, if there's not a perfect square as a factor, that's as far as I can go. But if I can pull something out, can I pull something out here? Here. 4 would work. So the perfect square, just like before, when I would have, like for instance here, it would be 2 square root of 2. But this I is out there to hang out with that 2. It doesn't technically, but it's sort of one of those things where I could write x4 or 4x when I'm doing algebra. This is kind of just the way that we look at it more often, is that the I would go in front with that, but it definitely has to be out from underneath the radical. What about this last one once I pluck the I out? Okay, 16 and 2. I've got to make sure I'm getting the biggest one. Because that's one thing I noticed when I was going through homework checks last night, is on the radical sheet, some of you are good at getting some of the breakdowns, but you aren't necessarily getting the biggest one every time. Why would it matter? Well, here's kind of the way of looking at it. When you're breaking down radicals, true, if you had something like 4 times the square root of 2 or 2 times the square root of 8, if you punch those into the calculator, you get the same thing at the end. But it's one of those things in math, sort of like if you have an answer on a quiz and you write x equals 3/9, which you know reduces to 1/3 in its most simplified form. we're kind of really picky in math about being as simplified as we can, because there will be a point where we start using these radicals in like fractions and reducing equations that if you don't reduce it to its simplest form, you're not going to see where it can simplify more. So that's why we really want to work on getting the biggest ones of these, especially as we start working through more of them. Okay? Sure.
So on the fractions, we always have one of them on the outside.
Yeah, if you always are looking to do your pair, it's whatever one's the perfect square that we're doing. So like when we had that list of when we had 4 and 9 and 16 all across there, whichever number in the list that is, that's the one that's going to go in front once we break it down. Okay? Good, good, good on the questions. Bump this up a little bit. Now these look similar to what we were just doing in the last section. Same idea is working here. We've got to work on getting x squared by itself. So what would I need to do first on this one? Okay. So if we minus the 10 here, and then divide by 3. Once I isolate my squared term, that's the point where I can do my square root. I can't always do it as the first step. Once I get to here, there's a couple of things I have to keep in mind. Again, whenever you have a squared, a quadratic equation that you're solving, you're going to get two answers, unless the answers happen to be the exact same number. So I know it's going to be plus or minus. Okay? Because the 12 breaks down to 4 and 3. We know we'll deal with the negative by pulling out an I in a minute. So square root of 4 is 2, and I have to pull out the I to get the negative out. And if for some of you, you need to take that one step here, if going here to here you think might get you, some of you at this point may have to go and say, okay, x squared equals plus or minus I square root of 12, and then break it down. If that's the extra step you need to be able to get the right answer, do it, okay? Some of you, that's just one extra step. You're like, no, I don't want to do that. So it depends, just person to person. But this is going to be consistent all the way through. Get the 26 out of there. Again, most of the things in this class are about details. Sometimes it's the little things that can get us if we're not careful. Get to our square root here. And again, just as a reminder, and I'll actually do it this time, we know it's plus or minus. I know I have to pull out an I. So that's what I'm looking at this point. Okay, so now there's two things to remember with the quadratics, the I and the plus minus. What's 18 going to break down into? 9 and 2. And again, the perfect square, the 9, is what's going to break down and go with my I. So 3i, and then the 2 is still stuck here. So we're kind of combining things here. We're breaking down a radical, 3 square root of 2, and solving for a quadratic where we have plus and minus. Now it gets a little different on 3. What do I have to do first on 3? Okay, we're going to multiply through by negative 2 because it lets us do two things. One, it lets us cancel this fraction out, and the negative takes care of the negative up here with my 1. So all I'm left with is my quantity, my x plus 1 squared. So can I just minus 1 next? Right. This is different than 2. This isn't in parentheses. I can minus the 26. This is in parentheses. That's a quantity. They're stuck together right now. So I've got to square root it first. Then again, plus or minus. Pull out the I. Put my 10. Can I break down the 10? No. Okay, there's not a... I mean, I know that 5 times 2 is 10, or 1 times 10 is 10, but I don't have any perfect squares to work with. So all I'm going to be able to do now is subtract the 1. Now be careful. Right, this doesn't go with the I. The only time we put something directly with the I is if I can factor, I can break down, my perfect square. So negative 1 plus or minus I plus square root of 10. So my form is going to look a little different depending on if I can break down the radical. Okay, that'll go with my I. But if I can't, whatever comes over, okay, is just going to sit there in front. And we really want to work on keeping it in that form. All right. Anything so far? Take a minute, kind of look it over. Let it sink in a little. If there's anything you're wondering about, let me know, because I want to make sure that we're good to go here. We're actually getting to a little bit easier of a part here now. Okay. So when adding or subtracting complex numbers, the real parts combine, the imaginary parts combine. So here, okay, that plus, I'm just combining like terms here. Don't make life difficult. 4 plus 3 is 7. Negative I plus 2I is plus I, and I'm done. Now some of you are going to say, can I put I plus 7? You could, but again, when we're doing math and we talk about putting something in standard form is my constant term, my plain old number, plus whatever I have. So again, this is the correct form, is the way that you're seeing it in number 11, the way we're going to see it for the rest of these works across. The only thing really we could mess up here is if we're not careful when we distribute. Good. Nothing happens in the first set. Signs change in my second quantity, my second set of parentheses. And then again, we're just looking for things that are alike. 7 minus 1 is 6. Negative 5 plus 5 cancels, and I just end up with 6. So we're kind of back with Algebra 1 with combining like terms. Here, be careful. That minus, again, distributes through, so changes this to a positive. Changes 9 to a negative. And again, that plus means nothing changes over here. And then just like on the last one, find the things that are alike. 8 minus 8, okay, that all goes away. Negative 9 plus 4 is negative 5. Again, just leave things be. Don't make it complicated. But you're going to have to watch, because we're going to get to a point where we're going to be multiplying those. And so somebody's going to see the parentheses, but, ooh, I multiplied. Watch, if there's a plus or a minus in the middle, you don't have to go to all that work. So, as we flip over, right, the expression is a complex number. Now, notice, no more plus or minus between the parentheses. So now when I distribute, and I simplify, negative 10i plus 5i squared, we have to make note from something we had on the front. Yes, that I squared equals negative 1. So if I ever see an I squared now, I'm literally going to replace that portion of my expression with negative 1. Notice it's not negative 1 squared, because it's I squared that equals negative 1. So the I squared gets replaced. And at this point, again, I want to write it in standard form. So 5 times negative 1 is negative 5. The negative 10i is still there. Again, not incorrect if you wrote negative 10i minus 5. It's just one of those math detail things again. But I may not have to do that every single time. If I distribute through, and I don't end up with any I squared terms, I'm done. So don't think every time you're multiplying, oh, something's got to be up. Not necessarily. But if you do get into a situation where you do have an I squared, and some of you will start figuring out there's a shortcut to this. So I distribute, right. Basically, all I'm going to do with the part that has I squared is, it says minus 15I squared. Well, if I replace I squared with negative 1, I get positive 15. So like Ben just mentioned, basically what's happening here is whatever your I squared term is, you're just changing the sign and losing I squared. Plus 5I squared becomes negative 5. Negative 15I squared becomes positive 15. And it just becomes a way to kind of make things a little bit simpler. 17, 18, and 19. We've got to FOIL these out. So again, you start to take a peek. You're like, all right, 7 times 2i, that's 14i. Then my outer, so we got outside, inside. Oops, first outer. Oh my gosh, Harty. 7, negative 1, negative 7. And again, you can do them in any order as long as you get all of them. Negative 4i, 2i, negative 8i squared. I have this guy left in the middle because I kind of went out of order. Negative times negative is a positive 4i. So I start to look at that. I go, okay, I know I squared is negative 1. So this right here is really a positive 8. Because negative 8 times negative 1 is positive 8. So negative 7 plus 8 is 1. 14i plus 4i is 18i. So I'm just FOILing, and wherever I see the I squared, I'm replacing it. Same is going to happen with these last two. If I do my firsts here, 6 times 6 is 36. My outer is negative 18i. Inside, 3 times 6 is 18i. And my last, 3i times negative 3i is negative 9i squared. Again, this equals positive 9, because again, negative 9 times negative 1. And once I have that, I'm just going to combine like terms. 36 and 9 is 45. Negative 18i and positive 18i cancel. Ends up being 45. No i's, no I squared, just 45. So again, keep that part simple. And I always want to do one like 19, just because I know what's going to happen most of the time. A lot of times people just square the 3 and the 4i and think they're done. So here's what I'd want you to do here. For most of you, it's going to be a good idea to literally write this out. 3 plus 4i squared means I have 2 of these. And then I can FOIL it out, because otherwise I think you're going to probably lose the middle term. So my first term, 3 times 3 is 9. Outer, 3 times 4 is 12i. My inner terms, 4 times negative 3 is also, 4 times positive 3 is also 12i. And then I have plus 16i squared. But again, I know better. I know that 16i squared just means I changed the sign. So that's really just negative 16. So 9 minus 16 is negative 7. And 12 plus 12 does not cancel. It gives me 24i. And so again, it's a patience issue. Foiling you've done, combining like terms you've done, now it's just adding that little I squared component into things to try and make life a little bit easier. Another thing that we've done before we're going to get to add to. Complex numbers. A plus bi and a minus bi. Remember last section when we'd have a radical in the denominator. We multiply the numerator and denominator to rationalize it by that same square root. We're going to do that here. So here's how this is going to work. I can't have I in the denominator. I'm actually going to write that down. Okay, I can't have I in the denominator. It's just a no-no, like having a square root in the denominator. Can't do it. So to fix that, whatever I see down in the denominator, I'm going to change signs on it. Here's what I mean. 1 minus 2i, if I want to get rid of it, is going to be 1 plus 2i. You're like, now, why is that? It sort of works along the same concept as number 18 does up here. Notice 6 plus 3i, 6 minus 3i. I got to the end, there were no i's left. Same thing's going to happen here, and I'll teach you a way to make this go faster. Up in the numerator, I'm actually going to write this out below it, so we've got a little more room to work with on this first one. We're going to FOIL it out, at least in the numerator we are. 5 times 1 is 5. 5 times 2i is 10i. 3i times 1 is 3i. And 3i times 2i is 6i squared, which we know is going to be negative 6. And we'll talk about that in a second. You'll see in a second here, because what I'm trying to do is, I'm trying to eliminate I in the denominator. And so here's how this is going to work. When I FOIL this out by using the opposite sign, or its inverse, let's see what happens. 1 times 1 is 1. 1 times 2i is 2i. Negative 2i times 1 is negative 2i. And negative 2i times positive 2i is negative 4i squared. And you're like, Harty, I still see an awful lot of i's all over the place. I understand this, but you won't very soon. So as was mentioned, the 6i squared, we know actually equals negative 6. Because I squared is negative 1 times negative 1 is negative 6. So 5 plus negative 6, negative 1. 10i and 3i, 13i. But watch what happens down below. Negative 4i squared is actually positive 4. So again, it just changes the sign and makes the I squared go away. So 1 plus 4 is 5. 2i minus 2i. Sweet, there they went. I've rationalized my denominator. The only way you can do that is by multiplying by the inverse. And the only way I can do that here, you're like, why don't you just do it down here? If I only did it in the denominator, I'm changing the value of the answer. If you take anything and divide it by itself, it's really like multiplying by 1. And that's kind of strange, but it's true. So when you're doing any of these, if I have a plus in the middle, I change it to minus. But here's where I'm going to learn my shortcut. Because if I look at this for a minute, if I look back at 20, I'm like, well, 1 times 1 is 1. 2 times 2 is 4. 1 plus 4 is 5. I wonder if that works here. 1 times 1 is 1. And that's going to be 1. I wonder if this is going to end up being 2. Let's find out in a minute. We'll work this out. We'll see how that works for us. So here, 2 times 1 is 2. Negative I times 2, negative 2i. Negative 7i times 1 is negative 7i. Negative times negative is plus 7i squared. And if some of you get to a point where you can mentally think about that and go, oh, that's going to be negative 7, go ahead and change it to that right away. But for now, we'll just kind of make mention of that to ourselves. Down here, let's see. So 1 times 1 is 1. Negative 1i and positive 1i are going to cancel. That's always going to happen down below. Those middle two terms will cancel. So I'd have 1, and then I times negative I is negative I squared, which I know negative I squared is positive 1. So it does turn into being 2 down there. So that's a way you can shortcut it. You really only have to do the F and the L of FOIL down in the denominator because the OI in the middle cancels. So here, 2 minus 7 is negative 5. Negative 2 and negative 7 is negative 9i over 2. Yeah, if you had an I squared term that had a negative, it would become plus, right? And if it's a positive I squared, it becomes negative. We're just switching the signs. Yep. And then the last type you can get thrown at you. You're like, ooh, what if it's just plain old I? How do I deal with this? Do its inverse. If it's positive 3i, I'm going to do negative. Actually, not going to have as much work on this one. There's the first. Yeah, so negative 3 times negative 2 gives me 6i. 5i times negative 3 is negative 15i squared, but we remember what that's going to be. And this is going to end up being negative 9i squared. But again, remember, a couple of little things here. I squared means that sign's going to change. That's going to become positive 15. That sign's going to change with my I squared, makes it 9. Here's a new twist. Is there anything that divides into all three of those? 3 does. If you can reduce the fraction by dividing through by 3 in this case, you have to do that. It's not like factoring in that it's not like I'm going to put the 3 out front. This is more like reducing a regular fraction, like 3 over 9 to 1/3. But only if you can get it out of all 3 of your parts. Say that one more time. If I put zeros here, but if I put zeros here to wipe everything out, my answer would end up being 0. I couldn't do it with 0 for that. Nope. Nope. Now the fun twists. They're like, where is this ever used in real life? Here it comes. Electrical circuits. Okay? Resistors, inductors, capacitors. Okay? Lots of fancy language, but a much simpler concept. So let me explain how this works. To find what's called resistance in an electrical circuit, which is kind of important so people or things don't get overpowered or electrocuted. It's called impedance. So you're going to add these things together, your resistance, and there are actually imaginary numbers involved in electricity. Okay? You're not going to have to memorize the formula. I'll guarantee that right now. So to find this impedance, here's how this works. Z is going to equal my resistor which again, I'm always going to give you all these values, plus the inductor. Okay, the inductor is what Li is. So that's just going to be 10 ohms. And then C, okay, oops, I forgot my I. Excuse me. And then the C, my capacitor, also has an I. So that's going to be plus 5I. Oops, no, Harty, follow the formula. Watch your details. So all I have to do here is combine like terms, and I'm going to be done. So here, I only have one term that doesn't have an I on it. The 6 at the beginning. So I've got 6 plus, if I have 10 I ohms, and 5 minus 5 gives me 5 total. And it's kind of the funniest looking thing you'll see. But you've got it this way. You may see it written, since they're both in ohms, you may see it written as 6 plus 5I ohms, but these are the same thing. Okay? You can use either one. If they happen to give me 2 inductors, okay, because sometimes the circuit will have that, depending on how complex it is, I'm still just going to follow the formula. So R is my resistor. There's no I with that. So that would be 13 ohms. Plus, now you're like, okay, so Li, so there's 2 of them this time. How does this work? I just put an I with each one. Or I can add them up right away. So 4 and 5 would give me 9. And you could write this as 9 I ohms instead of putting the I on the outside. That would work too. And then minus, this is my capacitor. Okay, just to show we can write it either way. And for a lot of you, I think it would probably be easier to put the I with the coefficient. So when I get done, again, the first term is going to be the only one that doesn't have an I with it. And then 9 minus 7 is 2. And again, you can leave it this way, or you can factor out the ohm and write it as 13 plus 2I ohms. Either one, again, perfectly acceptable. But it's just, again, it's not, you're not necessarily going into electrical work, but it's letting you see that this actually does come into existence. And finally, down here at the bottom, okay, we now, before we couldn't do a sum of squares. We could do a difference of squares. Okay, if we had something like x squared minus 9, it would be x plus 3x minus 3. Now with these, it's the same idea, except if you think about it, let me scooch this over so we can kind of look at a different example here. If I had x squared minus 9, okay, we did that before. It was x plus 3, x minus 3. Here's the only thing that's going to change. If there's a plus in the middle, we're still going to have the 2 sets of parentheses. I'm still going to have the x and the 3. I'm still going to have the plus and the minus, except now an I goes with it. You're like, well, what's up with that? Why is that? Let's get these last 2 written out, and I'll show you fully out on 26 why that is. Same thing here. What do I square to get x squared and to get 49? 7. So x plus 7I. And that's the only thing you've got to remember. If it's a plus in the middle, I've got to use I. Now, after this last one, we're going to see why this works. What about these 2? 5x and 1, or 5x and I. You can put the 1 in front of the I if you want to. So here's how this works. You're like, why does this work this way? Well, oops. I forgot my minus. If I FOIL it out, let's see what happens. 5 times 5 is 25x squared. Okay, that makes sense. That should happen. Minus 5xi plus 5xi. They cancel each other out. So then you get to the end, you've got minus I squared. But I squared being negative 1 just changes the sign. 25x squared plus 1. I get it back. Okay? So that's how that works out. So again, so if you were actually, well, you'll just be asked to factor something like this. I'm still looking for this. I was just letting you see where it actually comes from. Trying to make sure I get the question. If this is the question, factor this. This is what I'm going to see for your answer. You don't have to show me this. I wanted you to see where this is coming from, how this actually equals that. Yes. Okay. So, what you've got